Hi everyone, my name is Guochao Jason Sun, a postdoc based at Northwestern University. So today it's my pleasure to share with you some recent works I did with my collaborators on the physics and implications of bursty star formation in high-Z galaxies, so mainly from the fire simulations. Oops. So basically, using a suite of high-Z Fire 2 simulations, we're looking into the UV variability of galaxies at cosmic dawn due to bursty star formation, and we want to know like how this may be related to the observed abundance of UV bright galaxies at cosmic dawn, basically. So from this example, you can see that the star formation history of high-Z galaxies is highly bursty in our simulations that can spatially resolve the star formation and stellar feedback. And by matching the star formation history and the mock images on the right, you can see that the burst cycles of star formation can actually drive strong fluctuations of the galaxy brightness and therefore the observability in the rest frame UV regime. So in terms of galaxy abundance, we can actually calculate the UV luminosity function from our cosmological zoom-in simulations by taking the full distribution of the UV magnitude and halo mass for our individually simulated galaxies and convolving with the halo mass function. And in order to gauge the specific kind of impact of bursty star formation on galaxy abundance, we defined two contrasting scenarios. So in the bursty case in red, we essentially evaluate the UV magnitude from the true ages of star particles in our simulations. And we did something different in the smooth case in blue, where we manually smoothed the star formation history on purpose by redistributing the stellar age distribution in order to smooth out the SFR fluctuations over some prescribed time scale. So from the comparison in terms of the luminosity function, you can see that our simulation result can actually provide a very good match to observations all the way up to redshift 12. And it turns out that bursty star formation plays an important role in shaping the bright end of the UV luminosity function, as you can see from the difference here, which can be order of magnitude. So one thing I want to note here is that our simulations, as I show here in the bottom right, actually predict normal galaxy scale integrated star formation efficiency. And in order to see why this is the case, we can take a closer look at the star formation in gaseous halo in our simulation. So here, as you can see in the top left, the multi-phase gas in our simulated high-redshift galaxies is characterized by large temperature and density fluctuations. So due to strong stellar feedback, the gas doesn't really form a disk, like often assumed in analytic models of galaxy formation, including in the high redshift. So basically, instead of like forming a disk, the gas distribution is characterized by it's basically very morphologically disturbed, and the kinematics is highly dominated by turbulence. So if we look at the ongoing star formation instead, we can see that the ongoing star formation is very much restricted to the cold and dense gas, and spatially it extends out to very large halo radii. So if we look at the distribution of gas density contrast, as I show here in the two bottom panels, we can see that the distribution is well characterized by one single broad PDF that is roughly log normal across all halo radii. And the color coding here suggests that the star-forming gas is very much restricted to the very dense end of the distribution, and it comprises only a small fraction of the total gas mass. So this motivates us to basically describe the gaseous halo as some kind of density field of turbulent flows, which allows us to put together some like simple analytic approximation for star formation. So specifically, we can consider the profile of mean gas density and combine it with the PDF of the density contrast plus some threshold or density cut for star formation to happen. And by combining these simple ingredients, we actually see that we can actually come up with a fairly good analytic approximation for the star formation rate as a function of halo radius measured from our simulations. So this basically provides an explanation for the normal SFE from our simulations, which is basically due to the large density, the broad density distribution, which makes the mass fraction of star-forming gas actually small, even though the SFE per free fall time can be high. And this also provides us a physical perspective to model high redshift galaxy formation without assuming an equilibrium disk. Thank you.